linear differential equation of second order with variable coefficients. Let's see how to solve this. There are different methods. We'll look at each one of them one by one. But first let's see how the general form of a linear differential equation of second order with variable coefficients looks like. So it looks like d square y by dx square plus p dy by dx plus qy is equal to s, or it could also be written as y2, where 2 represents the second derivative, plus p y1 plus qy is equal to r. Now here p, q, r are functions of x. Okay, there are various methods. So let's look at the first one. Complete solution in terms of known integral belonging to the complementary function. Okay, so let's begin. Let's write this again. D square y by dx square, second derivative, p dy by dx plus qy is equal to r. Now remember, we are talking of in terms of known integral belonging to CF. So let y is equal to u be a known integral in the complementary function of the above equation. So if we do that, then y equal to u is a solution if r equal to 0. That is, the right hand side is equal to 0. Okay, so just follow the logic. So let the complete solution of d square y by dx square plus p dy by dx plus qy equal to r be y is equal to uv. Remember, y is equal to u is a solution if r is equal to 0. So here we are saying that if we multiply it by v, then we get a solution in case r is not equal to 0. Now here v is a function of x. Okay. Now let's differentiate this. We get dy by dx is equal to, product rule we apply, u as it is dv by dx plus du by dx times v as it is. Now let's differentiate it once more. We get d square y by dx square is equal to, now we have to apply the product rule for each of these terms. So u as it is d square v by dx square plus then du by dx times dv by dx as it is plus du by dx as it is times dv by dx plus v as it is d square u by dx square. Yes, so this becomes u d2v by dx square plus 2 times du by dx times dv by dx plus v d2u by dx square. Now let's put y is equal to uv in our original equation. So d square y becomes uv by dx square plus p d by dx of uv plus q uv equal to r. Okay, now let's do the necessary substitutions, because We have already evaluated these terms. Yes. So u d square v by dx square plus 2 du by dx times dv by dx plus v d 2u by dx square. So this is our first term. Now the next term is p times u dv by dx plus v du by dx. And then we have q uv equal to, now remember, if we take r is equal to 0, that means right hand side is equal to 0, then we said y is equal to u is a solution, right? So which means d2u by dx square plus p du by dx plus qu is equal to 0. Okay, so we will use this fact in this. So what will happen? Let's open up the bracket. So u d square v by dx square plus 2 du by dx dv by dx plus v d2u by dx square plus pu dv by dx plus pv du by dx plus qu plus qv is equal to r. Now here we have to figure out this. So to figure out that, let's first identify where this is. This is there here. Du by dx is here and qu is here, right? So let's take them together. d2v by dx square plus 2 du by dx times dv by dx plus pu dv by dx plus qv plus, now let's take those three. Now if you notice v are common. Actually I should not have done that, so let this be v, right? So v is common to all the three, so let's take it out. What are we left with? d2u by dx square plus p du by dx plus q u equal to r. Yes, so which means that this entire thing is 0, right? So these three terms add up to 0. We are left with d2v by dx square plus 2 du by dx times dv by dx plus pu dv by dx plus qv equal to r. Now if you notice that this qv is here also and here also, so actually qv goes into this, right? V is there here, QUV, so we don't need that here, there, so which means we don't need it here. So this is equal to R. By the way, this should be implies. Okay, now d2v by dx square plus dv by dx is common, so let's take that out. 2 du by dx plus pu equal to R. It is still second order, right? So let's do one more substitution. Let's say z is equal to dv by dx, right? So if we do that, what happens? dz by dx is equal to d2v by dx square. So now we can do the substitution. Implies u d square v d2v by dx square is dz by dx plus dv by dx is z. Then we have 2 du by dx plus pu is equal to r. Okay. So now that second order has disappeared. Now let's put it in the standard form. That means this should disappear. So to make it disappear, let's divide the whole thing by s. So these two cancels out. So dz by dx plus z by u, 2 du by dx plus u. Now let's do one thing. Let's take this u inside. Let's take this u inside. So this becomes u. This u gets cancelled. So r by, so this is a first order linear differential equation and we know how to solve this. Remember, to solve this we use integrating factor and that we multiply it with both sides. So here the integrating factor would be e to the power of integral of 2 du by u dx plus p, e to the power of, first term when we integrate we get 2 constant as it is, 1 by u is log u, right, plus integral of p dx as it is. Now using the laws of exponents we can split it up to log u times e to the power of integral of p dx. This can be written as log u square, e and log gets cancelled, integral of p dx, which means u square e integral of p dx, right? So that is the integrating factor. Now we go back to our this equation, dz by dx plus 2 by u du by dx plus, am I right, plus p, and then what do we have, is equal to r by u, is equal to r by u. Did we miss anything? Yes, z is also there. So z is also there. Okay. Now this integrating factor we multiply both sides. Yes, e to the power of integral of p dx. So what happens? We get u square e to the power of integral of p dx dz by dx plus 2 du by u dx plus p, z times u square e to the power of integral of p dx is equal to r by u times u square e to the power of p d. Okay, we have reached till here. Now what else do we need? Shall we open up this bracket? Let's open it up. U square e to the power of integral of p dx dz by dx plus 2 du by dx. Here, okay, u z u square e to the power of integral of p dx plus pz u square e to the power of integral of p dx is equal to r, this u and this cancels, r u e integral of p dx. Okay, so we have reached this. Here u and this square get cancelled, right? Now comes the challenging part. How do we, what is the next step going to be? Now you never lose sight of what you are trying to achieve. What we are supposed to get is v, for which we had dv by dx, which we said we converted into or substituted with z is equal to dv by dx. And then we said dz by dx. So we require z is equal to, right? Okay, so which means we have to integrate. Now we can't just integrate this, we have to integrate the left hand side and the right hand side. So integrating both sides, what do we get? Now this is the tricky part, the left hand side. So let's see how do we integrate this. Um Look at this, all the three terms, and see whether you can recognize a pattern. And then based on that pattern, it might be right or wrong, that's a different thing. Write it down. What you think is the integral. And then you differentiate it to get back this. If you get back this, then you are right. So here you have u square. Here you have z, right? And here you have p e power of integral of p dx. Yes? So see here, u square. Here it is integral, a differential of u square. That is 2u du by dx, right? The other two terms are e to the power of p dx by dz by dx. Okay. Now, here if you look at it, dz by dx, here you have z. So, z's differential is dz by dx. And e to the power of integral of p dx, if you differentiate it, what do you get? P times e to the power of integral of p dx. So, which means these three terms are as if we applied a product rule to a expression. And that expression most likely is u square z e to the power of integral of p dx. So what I'm saying is that this is the integral of the left hand side. Now how do we prove it? Look at this. U square z and e to the power of p dx remains as it is, right? No. U square e to the power of p dx remains as it is. Z is differentiated, dz by dx. In this case, z remains as it is, e to the power of p dx remains as it is, u square is getting differentiated, 2u du by dx, right? And here z remains as it is, u square remains as it is, and this is getting differentiated. E to the power of p dx will give you what? E to the power of integral of p dx times the differential of p dx, that is p. So that is there here. Okay, so that is the integral. And on the right hand side, you have to integrate e to the power of integral of p dx dx and the constant of integration. Remember, we want z only in the left hand side. So z is equal to 1 by u square e to the power of integral of p dx integral of ru e integral of p dx dx plus C1. Now remember, Z is nothing but dV by dx. This is a substitution that we had. Okay, so this all becomes u square e integral of p dx, and this we have to put it in the bracket. Yes, because when we bring it to the this side, it is applicable to both. Okay, so integral of ru e integral of p dx plus c1, and once we have done this, we have got dv by dx. Now what we want actually v. Remember, y is equal to uv, so you already, we know v we have to figure out, and that we can get by integrating again. So integrating dv by dx, we get v is equal to integral of e to the power of minus, if we bring it to the numerator, it becomes minus by u square within brackets integral of RU e to the power of integral of P dx plus C1 plus, since we have integrated it again, C2. So this is V. Remember, our solution is V, y is equal to U times V. So this would be equal to U, which we assume that is the solution, and V is this. So this is integral of e to the power of minus integral of P dx by U square, then within brackets again an integral of RU e integral of P dx plus C1 plus C2. This is the complete solution. Now there might be a case where RHS is equal to 0, that is R is equal to 0. In that case, what happens? The only thing is this equation actually gets this y is equal to this solution becomes much more simplified. So dv by dx is equal to, here if you notice, dv by dx, r is equal to 0, so the whole thing will become 0. We will be left with only c1 by u square, right? So we will be left with c1 e to the power of minus integral of p dx by u square, and to get v we have to integrate it. So v would become c1 times integral of 1 by u square e to the power of minus integral of p dx plus c2, right? And this is variable separable form. We can solve it using that method. So in this case, the complete solution would be y is equal to uv, which is equal to u times c1 integral of 1 by u square e to the power of minus integral of p dx plus c2, right? So this is in case right hand side is 0, and this is in case right hand side is a function again. Okay, in the next video we will look at solving one problem on this second order linear differential equation. That's it for now. Bye.